I just realized as I looked at this that I'm catching my mistake from the last problem, because while this is the correct antiderivative, 2x minus x squared over 2 plus 2x cubed over 3 minus x to the fourth over 4, I am missing, to be completely correct, I am missing my plus c. And in all of these antiderivative problems, or these indefinite integrals right now, whenever you get your final answer, make sure to be completely accurate, you do put a plus c in there. Okay, example 3. Let's do example, I'm going to do example 3 just right over here. Example 3, I've got the antiderivative of 1 minus 2t cubed all over t cubed. So do you remember when we did derivatives, how we would try to simplify our functions before we started to use the power rule? It goes the exact same way with antiderivatives. And so I would rewrite this as the antiderivative of, it's going to be 1 over t cubed. And this is because I've got a single term in my denominator. So I can say 1 over t cubed minus 2t cubed over t cubed. Or in other words, this is the antiderivative. 1 over t cubed is t to the negative 3. And minus 2t cubed over t cubed, so that would be minus 2 dt. And the reason this is dt is because my variable of integration here is t. So all I have to do is follow my rule. Now it gets a little weird when that's a negative exponent. In the last video I was saying when it's, t to the third, it's t to the fourth over 4 for the antiderivative. Or if it's t to the fifth and you're doing the antiderivative, it would be t to the sixth over 6. A little bit tricky with these negative exponents. Remember that we are adding 1 to this exponent. So when you add 1 to negative 3, that's actually going to give you negative 2. And we are dividing by that number in the front. So you end up with t to the negative 2 divided by negative 2 minus, what function has 2 as its derivative? Well, that would be 2t. And then, of course, put in our plus c. So one thing that you could potentially do in simplifying this is, you see we have t to the negative 2 divided by negative 2. You could take that t to the negative 2 and make that t to the positive 2 in that denominator. But we can also, at this point, we can leave it like that. Okay, example 4, I'm going to do it in this space right up here. Remember, if you can't apply the power rule right now, you're looking for a function that is somewhat similar to what you've worked with before when doing derivatives. And here, yes, we've got a cosecant of x and sine of x, cotangent of x, and we worked with those before, but you see how the cosecant of x is outside these parentheses? Definitely makes sense in a case like this to distribute that cosecant through. Let's simplify this and see where it takes us and then do our antiderivative. So cosecant of x times sine of x. Now cosecant is the reciprocal of sine, so cosecant times sine is actually going to be 1. And then cosecant times cotangent. I'll just write that down right now because I'm not quite sure what that would simplify to in my head. But I do know that cosecant of x times cotangent of x, I think, wasn't that a common derivative that we worked with in the past? What function had a derivative of cosecant cotangent? I think there was one. So we're going to work with this now. I think we don't have to simplify this one. It's going to be easy for us to work with. What's the antiderivative of 1? What function, and we're dealing with terms of x here, what function, when you take its derivative, gives you 1? That would just be x. And the function that has a derivative of cosecant cotangent, you might be looking at your table or your sheet of derivatives and all that. That function was cosecant of x, but not exactly cosecant of x. The derivative of cosecant of x before was negative cosecant cotangent. So the correct antiderivative of cosecant cotangent is actually going to be negative cosecant of x, because if the derivative of cosecant of x is negative cosecant cotangent, then this negative negates the negative from the derivative to make it positive back in the integrand. So that would be your solution to number 4. X minus cosecant of x plus c. Okay, let's scroll down and do a few more here. So in number 5, I said let's solve the initial value problem, i.e. find the specific solution to the differential equation. So even though this looks like a completely different problem, it's really not. And I realize that I've got a little typo here. This should be dy over dx equals negative 1 over x squared. So what I'm saying is my derivative is negative 1 over x squared. Let's find the solution to this differential equation. In other words, what function of, in the form y equals will have its derivative as this right here, and it's subject to this condition. And so a lot of times what I do with this is I actually do the following. I bring the dx to the other side, and I know that might seem weird, but if you bring the dx to the other side, like this, where you say dy is equal to negative 1 over x squared times dx, and then I think about doing the antiderivative of both sides. And so on this side, if you're doing the antiderivative of 1 dy, in terms of the variable y, what function has a derivative of 1? Well, that would just be y. So this is going to be y equals the antiderivative of negative 1 over x squared dx. And I'm going to save a little bit of space here. Isn't negative 1 over x squared the exact same thing as, I'm going to be able to say negative x to the negative 2 dx. And you can see I'm saving space, but I'm also trying to write this in a way that allows me to use a power rule. And so the power rule would be, applied in this case, it would be, let's see, I'm gonna think, when I add 1 to my exponent, I'll get x to the negative 1. And now I have to think a little bit, because typically you would add 1 to the exponent and that number would go in front, but there's also this negative that's in front here. So I think this negative and this negative actually cancel each other out. And so if they cancel each other out, I almost wonder, is this function itself the antiderivative of negative x to the negative 2? I think it is, because if I did the derivative of this, wouldn't I get negative 1 x, and you subtract 1 from that exponent, that would take you to negative 2. And so I'm going to say plus c, and this is what I would call the general solution. This is the general solution to the differential equation. But I want the specific solution. So if I want the specific solution, basically we're saying let's plug this point into the function. 1's going in for x, 3 is going in for y, and then we can figure out what c is. And so if I plug in 1 for x, 1 to the negative 1 is just going to be 1. And I plug in 3 for y, then you'd have 1 plus c is equal to 3. So that means that the c value's got to be equal to 2. So you plug this in. I'm not writing it out right here, but you plug 1 in for x, you plug 3 in for y, solve for c, and as a result we would get y is equal to, we could write it simplified as 1 over x plus 2. And that's, again, because now you can verify it here. You plug 1 in now. 1 over 1 is 1, plus 2 gives you 3. We know that g of 1 is equal to 3. So that would be the solution to the differential equation, and we would classify that as the specific solution to the differential equation. Okay, example B. Same type of thing. Bring the dx to the other side. So you have dy is equal to x squared minus 1 dx. So we're going to do the antiderivative of both sides, and that's going to lead me to y equals the antiderivative of this. So y equals the antiderivative of x squared will be x cubed over 3. You add 1 to the exponent, divide by that exponent. And then what function has 1 as its derivative? That would be x. And then let's not forget our plus c. I'm going to plug negative 1 in for x and 3 for y. So if I do that, I get 3 times, this will be negative 1 cubed over 3, and then minus a negative 1 plus c. And so let's think about this. This would be a negative 1/3 plus 1, so that's 2/3. So we're going to subtract 2/3 from the 3, and that's going to lead us to c is equal to, well, that would be 2 1/3, wouldn't it? So 7/3. I think our c is going to be 7/3 in this case. So our solution our general solution was this one, y equals x cubed over 3 minus x plus c. Our specific solution to this would be y is equal to x cubed over 3 minus x plus 7/3. So the big difference between these problems where you're finding the specific solution or even a solution, general solution to a differential equation, and what I was doing above is above, do you notice that my answers are just expressions in terms of x? But down here, my answers are functions, y equals some function in terms of x. And so that's really the only difference. Okay, number 6. Find a function f such that the second derivative, that's f double prime of x, is equal to x plus cosine of x, and f of 0 is equal to 1, and f prime of 0 is equal to 2. So just as you could do derivatives multiple times, you could do antiderivatives multiple times. And so the first antiderivative we'll get would actually be f prime. So we can see that f prime of x would equal, what's the antiderivative of x, or x to the first? Hopefully you're saying it's going to be, you just up it and then divide. X squared over 2. Just like I was saying before, the antiderivative of x cubed, x to the 4th over 4. Or the antiderivative of x to the 7th, x to the 8th over 8. Try to get used to that pattern. And then the function that has cosine as its derivative would be sine. And then I would say plus c. And notice that this is my f prime of x function. So I can't plug this information in. I have to plug this information. So I have to plug 0 in for x into my f prime function and 2 in for y. So I get 2 equals, that'll be 0 plus the sine of 0 plus c. Well, what is c equal to? Well, I guess we need to know what sine of 0 is equal to. And I think the sine of 0 is equal to 0, isn't it? Sine of 0 is, yeah, because the cosine of 0 is 1. Sine of 0 is 0, so c ends up equaling 2. If c is equal to 2, then f prime of x is equal to x squared over 2 plus sine of x plus 2. Okay, so now let's do the antiderivative again. And one thing that I probably have not emphasized enough is when I see constants in front of powers of x, I apply the constant multiple rule with antiderivatives just as much as I do with derivatives. Because the antiderivative of x squared is x cubed over 3. The 1/2 is kind of just sitting out in front. So if the antiderivative of x squared, so if I just go over here for a second and say that that antiderivative is x cubed divided by 3, there's still a 2 that's down there, right? Or 1/2 that was in front of that. So the antiderivative of x squared over 2 ends up being x cubed divided by 6. The antiderivative of positive sine, remember the derivative of sine was cosine, but the antiderivative of sine is actually going to be negative cosine, because the derivative of negative cosine will lead you to positive sine. And then plus 2x, and then we'll have to say plus c. And then once again, we're going to plug in 0 for x, 1 for y. Let's see if we can do this here. So if we plug 0 in for x, this term goes to 0. You're saying minus the cosine of 0. The cosine of 0 is 1. So on this side, you're going to have minus 1 plus, that's also going to be 0 because you're plugging 0 in for x. So this term goes to 0. This goes to minus 1. This goes to 0. This is 1 on this side because f of 0 is equal to 1. So we have 1 equals 0 minus 1 plus 0 plus c. So you're going to bring that minus 1 to the other side and get c is equal to 2. And so if you just substitute 2 in for c, then this would be the specific solution to our function f. Okay, in the next video, we're going to look at the back of the notes. We're going to kind of visualize this stuff a little bit and also look at some applications.